In this tutorial, we'll pick up where we left off with the jumping problem, working with our force diagrams, and continue on to the next case of when the person is in the air. So just to review what we had covered before, we saw that when the person was starting to jump, they're moving in the positive direction. We defined our positive direction as up. They were also accelerating in that direction because they started at a zero velocity and started moving upward. And so because of this, we found that they had a net force going up, meaning that the force going up must be greater than the force going down. So we represented this with the diagram of the ground arrow pointing up being longer than the gravity arrow pointing down. When we go on to the next part of this, we'll see that the positive direction is still defined as the forward direction, or as the upward direction here. And as before, we know that there must be some gravity force acting on the person. So go ahead and draw that part in. We have a little bit of trouble figuring out what other forces are acting on the person at this point. And so again, it may be a good idea to come back to our idea of finding the net force. We can do this by finding the acceleration is, or at least some kind of representation to get an idea whether it's up, down, or zero. And then move from there to see if we can figure out something more about the individual forces. So let's set up our equation again to help think about this, because it's actually going to be a slightly trickier case than before. If we use our equation, so the same acceleration equation, meaning that final velocity minus initial velocity over time is going to give us the acceleration, we can think about what we might be starting off at and ending at for this particular case. Since we are moving up now, so the person is jumping up, they're probably moving upward at this point. This is soon after they have left the ground. And so we could say that the initial velocity is something like, say, 4 meters per second. So I put this in for the VI part, the initial velocity, and so that's after the subtraction. As for what might be possible for the final velocity, we know that as they are moving upward, they're going to start slowing down. They're not going to be moving upward as quickly. And so maybe I could represent this as 2 meters per second for the final velocity. The time here, again, it doesn't really matter. We know that time is going to continue in the forward direction. It's going to be a positive value. So I just put in, say, that this takes 0.2 seconds for them to, what we're showing here, slow down from an initial 4 meters per second upward to final 2 meters per second, still going upward, but not as fast. If we solve this, we'll see that it comes out to about 10 meters per second squared. But in this case, since we'll have a negative 2 on top divided by a 0.2 on the bottom, we're going to end up with a negative sign out in front here. This tells us that our net force is down here. We are getting a negative acceleration, and since the acceleration is in the downward direction, the net should be in the downward direction. So we'll add that to our diagram. What this means for the individual forces is that either the only force acting on the person at this point is gravity, or that there is some other force going upward, which is a possibility, but it's less than gravity. If we think about this situation a little bit more, we can think of the fact that the ground force was exerted because the person was in contact with the ground. They were pushing against the ground, and the ground was pushing up on them. Now that they're in the air, they're no longer in contact with the ground. Because of this, the ground is not able to push them upward anymore. This means that gravity really is the only individual force acting on the person. So at this point, our force diagram is actually complete. We don't have an upward force in this case because they are no longer in contact with the ground, and gravity is the only downward force. We can see here that the net force is also downward. They're accelerating downward now because as they move up, they slow down so that they're not moving up as quickly. And in this case, the individual force and the net force should actually be equal. This is because there's nothing that we have to combine with the gravity to cancel out any parts or add to them. So this completes our second force diagram, which now shows the person as they jump into the air.